Today I'm going to talk about capacitors with alternating current. Before I do, I want to review how capacitors act in DC, particularly how they act in charging and discharging cycles. And you might want to review the video I made about that, which I've linked below before you watch this, because I'm going to just give a quick overview of that. And it's important to understand how capacitors charge and discharge to understand why they do what they do in alternating current. So let's get started. I'm going to use the demonstration circuit I used to demonstrate how capacitors charge and discharge. I start with a battery, a switch, a resistor, our capacitor, and back to our battery. And I have another switch here just to facilitate showing that the capacitor is completely discharged when I start the charging cycle. So I'm going to start out with 1 volt, 1 ohm, and 1 farad because, first of all, they're easy numbers to work with, and they show a particular parameter of what we need to know about capacitors charging and discharging. So what I'm going to do is throw that switch, short the capacitor. Well, I have a resistor in series, but this will cause the capacitor to completely discharge if I leave that for a few seconds. Now I'm going to open that switch, and now I can start the charge cycle. So I close this switch, and what happens? Well, current surges over to the capacitor, but because the capacitor is two conductors separated by an insulator, that current cannot go through the capacitor, but it spreads out on to the plate that it reaches. Now, of course, what's really happening is we have electrons flowing the opposite direction. These electrons pile up on this plate over here, and they drive electrons off the opposite plate. But in this class, as is done in the electronics industry and most of academia, we talk about conventional current, where we pretend that the current actually flows the opposite direction because it's easier to analyze circuits if we imagine our current going from positive to negative, high pressure to low pressure. That makes more sense than trying to figure out what goes from more negative to less negative. That gets confusing. So we're going to stick with our conventional current. So the current flows into the capacitor. That drives current off the other side. Now, of course, it's not the same current, but we see current go in, we see current come out. It looks like the current's going right through the capacitor. And if we put a voltmeter here, we will see that that capacitor is 0 volts. Now this is the way it is at the moment we throw that switch. So what does it look like? We have current flowing through the capacitor, no voltage across it. That capacitor looks like a short circuit. So it might as well be just that, a short circuit. So at that moment in time, we have nothing but our 1 volt battery and our 1 ohm resistor, and of course we then have 1 amp of current flowing. So let's draw a quick graph over here of what's happening and what's going to happen. So at this particular moment in time, I've just flipped the switch, so our time is 0. Here's time on the horizontal axis of our graph, and our voltage and current are going to be over here. I'll draw that in later. So at the moment we throw the switch, our voltage is down to 0, and our current is at its maximum. And of course, in this case, 1 volt, 1 ohm, we get 1 amp of current, so I will put our 1 amp there. But after time, that capacitor starts to build up electricity, and it acts sort of like a compressed air tank. So a compressed air tank, you put a little air in, you get some pressure. You put more air in, you get more pressure. You put more air in, you get more pressure, and you can keep doing that until one of two things happen. Either you just can't push anymore, or the tank explodes. A capacitor works the same way, except of course our pressure is voltage. So we put a little electricity in, we get a little voltage. Put more in, we get more voltage. And we keep adding electricity, we keep getting more and more voltage until either we can't push anymore, or the insulation breaks down and the capacitor fails, and it could actually even explode. So as that charges, it starts to push back, so we start getting some voltage across it. After 1 second, in this case we have 1 farad and 1 ohm, and so we multiply those together to tell us how long it will take to get to 63.2% of our battery voltage, which of course is going to be 0.632 volts. So 1 farad, 1 ohm, 1 times 1 equals 1. That tells us 1 second to reach the magic number of 63.2% of that voltage. So there is, after 1 second, it's going to be a little curvier than that. It's kind of important to know that. So it starts to charge up. It's starting to slow down because as it charges, it pushes back more and more and the charging slows down. But after 1 second, we're going to get to 0.632 volts. And the current is going to drop down from 1 amp to 0.368 amps. So we start out at first, we have our maximum current and 0 volts. But as time goes by, in the case of these two resistors, that voltage is going to fully charge after about 5 seconds. So this is going to charge slower and slower and slower, and it's going to finally flatten out and stop charging when the capacitor reaches the source voltage. So it's going to reach 1 volt. It's going to stop charging, and our current has dropped down to 0. So what happened when we first flipped the switch, we have our maximum current and 0 volts. So when we have our maximum current, we have 0 volts, but then it climbs up and we have our maximum voltage, and now we have 0 amps. So when we have maximum amps, we have 0 volts. When we have maximum volts, we have 0 amps. Now, I'm going to redraw this to facilitate something I need to show here. Actually, I'm going to take this out of the way because I need a little more room to draw here. So I'm going to give ourselves a little more time, and we let that capacitor charge, and it charges up, and then it just stays there. Stays there at 1 volt in that case, or whatever the battery voltage is. So if that was a 10 volt battery, this would be 10 volts. If it was a 100 volt battery, it would be 100 volts. So it charges up to the battery voltage and then just stays there. And then the current starts at maximum, drops down to 0, and just stays there. So once the capacitor charges, it just stays charged unless we discharge it. So now I'm going to flip those switches. I'm going to open the charging switch and close the discharging switch. And this is going to start discharging. So what's going to happen? Let's do it right about there. When I hit the discharge, it's going to discharge following a curve that looks pretty much like the charge curve inverted. And in 1 second or 1 time constant, it's going to get down to 63.2% of the starting voltage. The current's going to do something kind of funny because, let me redraw part of the circuit here, or the whole thing actually. Well, I'll just, there, resistor and capacitor. And I'm going to be discharging. So I'll have this switch closed and that switch open. So when I was charging, current was flowing this way through the capacitor, but when I discharge, it's going to flow the opposite way. And so when it's flowing one way, that's positive current. Flowing the other way, it's negative current. It's rather arbitrary, but if I say negative current, that's all I mean. Positive current is flowing one way, negative current is flowing the other way, and we'll graph that as a negative current. So when I start the discharge, I open the switch, close that switch, it starts discharging. At first, this has 1 volt, so it looks like a 1 volt battery, and I have 1 volt and 1 ohm, so I get 1 amp of current. There's my 1 amp. But that current is going to drop back down, and eventually it's going to hit 0. So we're back to where we started with 0 volts and 0 amps. Okay, now let's let this stay charged for a while just to point out something. I'm going to redraw this with some more space so I can demonstrate something. So let's go ahead and let that charge. Oh, we'll charge it all the way, and current's going to go down to 0. And then I'm going to flip those switches and let it discharge. So this is going to discharge. That goes down to a negative current and comes back up. Then I'm going to flip the switches again. It's going to charge. So this is going to go charge again. The current's going to jump back up and then go back down. And so I'm spending more time with a high current. I have high current here, high current there, high current there. And it's going to do the same thing when I start the discharge here. So let's flip the switches even faster at a higher rate, at a higher frequency, and see what happens. So let's erase that to there. So right at this moment here, I flip the switch and let it discharge. So that discharges. That jumps down to negative, and I'm not going to let it discharge all the way. Now I'm going to start the charge again, and then I'm going to hit that's going to jump up to a high current and then drop back down. And then I'm going to start discharging it. Then I'm going to flip the switch again, and we're going to keep seeing this cycle. So if I flip the switches faster, I'm spending even more time in a high current state. So now let's flip them really fast. So I start to charge, and then I discharge. Start to charge, and then I discharge. Start to charge, and then I discharge. So I'm flipping those switches really fast, and of course the current is going to jump up to here, come down a little bit, then it's going to jump down to there, come down a little bit, jump up to here, come down a little bit, jump down to there, come down a little bit. So we have the current. Look what's happening. We're spending a lot of time with a lot of current. So the faster I flip those switches, or the higher frequency that I flip those switches and change them from charge to discharge, the more time I spend conducting current. So I get more current through the capacitor. So at a low frequency, I don't get a lot of current, but at a high frequency, I get a lot of current. So let's look at another device, which is just a resistor. And so if I get a lot of current, that means I have a low resistance. But if I get a small amount of current, I have a high resistance. So low resistance, high current, high resistance, low current. In the case of the capacitor, high frequency, high current, low frequency, low current. So that capacitor, as my frequency goes up, as I charge and discharge it more and more often, and let it go through less of the cycle, it conducts more current. So at higher frequencies, it looks like a small resistor or a low value resistor, and at low frequencies, it looks like a higher value resistor. So the capacitor changes its opposition to current flow with the frequency. The higher the frequency, the less opposition to current flow. The lower the frequency, the more opposition to current flow. We have a name for that. It's called capacitive reactance. And it's represented by the letter X and a sub C. So X means reactance and C means with a capacitor. And that's measured in ohms. So it's just like resistance. It opposes current flow, and it's measured in ohms, but it changes with frequency. Higher frequency, fewer ohms. Lower frequency, higher ohms. So that's the way the capacitor reacts to alternating current. Let's start taking a closer look at that. So let's put our source voltage on a graph. This graph shows one cycle of the source voltage. Remember that a sine wave is related to a circle, so we assign 360 degrees to our sine wave. Each vertical line represents 10 degrees on this graph. So we have 360 going from left to right with this complete cycle. Each horizontal line represents 20 volts. So let's put 0 volts in the middle, so the top is positive 100 volts and the bottom is negative 100 volts. Our 50 volt RMS source voltage peaks at approximately 70 volts. To calculate the capacitor voltage in real time would take some complicated calculus. There is a simpler way to calculate the voltage, but I don't want to tackle that right now, so let's just put the voltage here and analyze what it's doing. We'll join the show in progress right here, where the capacitor voltage is rising and just crossing 0 volts. Just as in DC, the current is flowing through the resistor and into the capacitor. The capacitor is charging, but as it charges, the source voltage is increasing. So the capacitor voltage is not leveling off like it does with DC. Right here, it's almost following a straight line. However, here the source voltage peaks and starts to drop. As long as the source voltage is higher than the capacitor voltage, the capacitor will continue to charge, but it starts to charge slower, so our curve begins to heel over. Finally, right here, the capacitor voltage and source voltage meet. After this point, the source voltage is lower than the capacitor voltage, so the capacitor begins to discharge. This is a key point in the cycle. The capacitor voltage will always cross the source voltage at the capacitor's peak voltage. If we reduce the resistance or the capacitance, the capacitor will charge faster and reach a higher peak voltage, but the capacitor voltage will still cross the source voltage at its peak. It has to. After this point, the source voltage is lower than the capacitor voltage and the capacitor will begin to discharge. Here we decreased the resistance or the capacitance, and the capacitor charges faster. The capacitor charges to a higher voltage and crosses the source voltage earlier, but it still crosses at the capacitor peak voltage. Here we increased the resistance or capacitance, so the capacitor charges more slowly and takes a little more time to charge, and the capacitor voltage crosses the source voltage later, but still at its peak. In the DC circuit, the capacitor charges until it equals the battery voltage. The maximum voltage across the capacitor equals the battery voltage. With an AC source, the capacitor voltage reaches its peak point at the time when it equals the source voltage. In AC, if you freeze time, the maximum capacitor voltage equals the source voltage at that time, just as in DC. The voltage across the capacitor is a sine wave. However, that sine wave is delayed compared to the source voltage. This delay time depends on the resistor-capacitor combination. Remember that we measure the points in a cycle of a wave in degrees, a complete cycle being 360 degrees. The delay in the peak of the capacitor voltage is a certain number of degrees after the peak of the source voltage. Let's go back to our circuit with our 30 ohm resistor and our 100 microfarad capacitor. At a frequency of 60 Hertz, we see that the capacitor voltage lags behind the source voltage by approximately 49 degrees. Remember that number. We will run into it later. In the DC circuit, when the capacitor finished charging, we had the maximum voltage across it and zero current. The capacitor was acting exactly what it is. It is two conductors separated by an insulator, so it's an open circuit. So at that time, we had our maximum voltage and zero current. Will it do the same thing in an AC circuit? Let's take a look. The current in the circuit is determined by the value of this resistor and the voltage difference across it. In the DC circuit, where we had a battery, which was 1 volt in that case, when we started charging the capacitor, we had 1 volt here and 0 volts there for a difference of 1 volt. That was a 1 ohm resistor, so we had 1 amp of current. But as the capacitor charged, this voltage rose and eventually it reached 1 volt also. And so if we have 1 volt here and 1 volt there, there's no voltage difference. Therefore, there's only 0 volts across the resistor. Remember that our voltage difference is what matters. So there's no voltage difference. That means 0 volts. And therefore, there was 0 amps of current flowing through the capacitor. In the case of the alternating current, we have voltages that are constantly changing. So this voltage is going up and down, and this capacitor is charging and discharging, reversing polarity, and then charging that way, then discharging. So these two voltages are going up and down, but they're not synchronized. One is going up and down at one time, the other one at another time. They're not synchronized, and they're not opposite each other. It's more like a little game here where one's coming and going, and so the voltage across this resistor is constantly changing. In the AC circuit, the source voltage and the capacitor voltage are constantly rising and falling. These voltages are not synchronized, so the voltage across the resistor is continually changing. This means that the current is constantly changing. The timing of this change is related to the source voltage and the capacitor voltage. Let's look at these voltages at different points in time and see what the current is at those times. We'll start here where the capacitor voltage is 0 volts. That's 50 volts on this side and 0 volts on this side for a total voltage of 50 volts and 30 ohms for the resistor. So we are going to get a current of 1.66 amps at that moment in time through the whole circuit, through the resistor, and therefore through the whole circuit. And this current is flowing through the resistor from left to right. We'll use a different graduation of our scale for current, otherwise it will be hardly visible. Let's make it 1 amp per vertical division. Now let's put a dot right here at 1.66 amps to represent the current at this point in time. Now let's look here where the source voltage peaks. The source voltage is at 70 volts and the capacitor voltage is at about 28 volts. That's 70 volts on this side and 28 volts on that side for a total difference of 42 volts. And that now gives us a current of 1.4 amps. Now let's look here where the capacitor voltage peaks. Here the source voltage is about 44 volts and the capacitor voltage is also 44 volts. That puts a difference of 0 volts across the resistor, so the current is 0 amps right here. Let's do one more right here. The source voltage is about 11 volts and the capacitor voltage is about 37 volts. The difference is now 26 volts. But now the voltage on the right is higher than the voltage on the left, so we go positive to negative here, so the current is flowing in the opposite direction, which we'll plot as a negative current. Now we have a current of minus 0.866 amps right here. Now let's put the whole current plot on the graph. The current lines up such that when the current peaks, the capacitor voltage is at 0 volts. When the capacitor voltage peaks, the current is 0 amps. No matter where we look, if the capacitor voltage is at its maximum, positive or negative, the current is 0. Likewise, the capacitor voltage is 0 wherever the current is at its maximum, positive or negative. This is true regardless of the frequency or the values of the resistor or the capacitor. This means that the current will always peak 90 degrees ahead of the capacitor voltage. Where does that put the current in relation to the source voltage? Let's figure that out. The capacitor voltage always peaks as it crosses the source voltage sometime after the source voltage peaks. The current always peaks 90 degrees before the capacitor voltage peaks. Therefore, the alignment of the current to the source voltage will be the lag angle of the capacitor voltage minus 90 degrees. In our circuit, the capacitor voltage lags behind the source voltage by 49 degrees. The current is 90 degrees ahead of the capacitor voltage. That puts the current approximately 41 degrees ahead of the source voltage. In our circuit, the current also has an RMS value of 1.25 amps. All of this finally shows us the relationship between the source voltage and the current. Let's relate that to a simple DC circuit. Let's say you have a 50-volt battery and a 40-ohm resistor. You'll have 1.25 amps of current. Ohm's law. Except there's one small problem. If we put a 40-ohm resistor across our 50-volt RMS supply, the peak current will happen at the same time as the peak voltage. However, in our circuit, the current peaks approximately 41 degrees before the source voltage peaks. This is because there is another source voltage, the capacitor, wreaking havoc with the circuit. We showed that the current peaks right where it should. Nevertheless, in this RC circuit, the current peaks before the source voltage by 41 degrees. It's the nature of the beast. So there we have it. In this particular circuit, the combination of the resistor and capacitor in series gives us approximately 40 ohms of opposition to current flow. Also, the current leads the source voltage by 41 degrees. Is there an easier way to tackle this? Yes. It doesn't explain why everything happens the way it does. It also doesn't demonstrate that an AC circuit acts exactly like a DC circuit at any moment in time, but it does calculate the opposition to current flow, the impedance in ohms, without any complex math. Just some simple algebra. We can also calculate the timing difference or phase angle between the source voltage and the current using a simple trigonometric function found on any scientific calculator. So let's look at those calculations. So here's our circuit. 50 volts RMS, 60 hertz, 30 ohm resistor, 100 microfarad capacitor. We just have to go through a few steps to find out the same information that we found out by simply plotting out all of the voltages and seeing how they acted at certain moments in time to get the current and its phase relationship to our source voltage. So we'll start by finding out how much opposition to current flow this capacitor has, and that's called the capacitive reactance. So we have our capacitance and we have our frequency, and knowing those, we can calculate how much opposition to current flow this capacitor has at that frequency. The formula is X sub C, the capacitive reactance, or the reactance of a capacitor, is equal to 1 over 2 pi Fc. So 2 pi is 6.28. F is the frequency and C is the capacitance in farads. Now we have to do the reciprocal because remember, as our frequency goes up, our capacitive reactance goes down. So as our frequency goes up, this looks like a smaller and smaller resistor. As our frequency goes down, we get more capacitive reactance. So this looks like a bigger and bigger resistor. So frequency goes up, capacitive reactance goes down and vice versa. So they are the reciprocals of each other. So to calculate the capacitive reactance, we need to take the reciprocal of these terms. So what we're going to do is take 1 over 6.28 times 60 times 0.0001. So to do this on a typical calculator, you hit 6.28 times 60 times 0.0001 equals, and I get a number that's kind of useless at this point, but now I take the reciprocal, so I hit the reciprocal button, and I get 26.53. So at 60 hertz, this 100 microfarad capacitor has a capacitive reactance of 26.53 ohms. So basically it acts like a 26.53 ohm resistor at this frequency. Of course, it's not a resistor, it's reacting to the frequency, it's not resisting it, because as we showed, the voltage across this capacitor is not happening at the same time as the current. So we have some things going on here that we have to take into account as we calculate the total impedance of the circuit. So we started out with that. We have 26.53 ohms there, and we have 30 ohms there. Now, can we just simply add these together like two resistors in series? No, we can't, because remember, the voltage across here is going to be 90 degrees out of phase with the current. So I'm going to draw a little graph over here. I'm going to draw a line about that long and see that's our resistance. So I make a horizontal line for the resistance, and that's going to be 30 units long. I can actually do this on graph paper and calculate this out by drawing a graph and just measuring the units, but we're going to do this by math. Now, to represent the capacitor, I need to make a line that's at a right angle to my resistance. Remember, the voltage and the current are 90 degrees out of phase, so that means I need to draw a 90-degree angle here, and that's going to be 26.53 units. 26.53 ohms, and my impedance is going to be the distance between these 2 points. And there's a really easy way to figure that out. It's called the Pythagorean theorem, a little bit of simple geometry. So the Pythagorean theorem says that the square of this distance is equal to the sum of these two squares. In other words, if I take 30 and square it, add that to 26.53 and square that. So I add those two together. I square it, add them together, and then take the square root. I will have the length of the hypotenuse of that triangle. So let's pull out my trusty calculator and do that. So that's going to be 30. Hit my square button. I'll store that in memory. Now I take 26.53, and I square that. Now I add that to what I just had in memory, plus recall. Hit the equal sign. Now I have a useless number, but now I take the square root of that number, and I got 40.04. So the length of this line is going to be 40, and that represents the impedance of 40 ohms. So I could do this on graph paper, and I'd find exactly the same thing, but I used the Pythagorean theorem to figure that out. So we already learned that this combination of resistor and capacitor is going to act sort of like a 40 ohm resistor, except the problem is the current through the circuit is not going to be happening at the same time as our source voltage. It's going to lead that source voltage, in this case, by 41 degrees. We figured that out when we plotted out all those voltages. So how do we calculate that angle? It's actually going to be this angle right there. So the angle of the current to our source voltage is going to be the angle of this triangle. How do we calculate that? Well, it takes a little trigonometric function. We're going to talk about that in a completely different video. I'll have some math review, but just for now, we just have to know that there's a little button on here that does this function, and the formula is, get this out of the way, our phase angle, represented by the Greek letter theta, is equal to the arctangent, which is the reciprocal of the tangent, which is a trigonometric function. I'll talk about those later. But what I can say quickly is that your sine and your cosine and your tangent are the ratios of these different sides. So The ratio of these two sides is the cosine. The ratio of these two sides is the sine. And the ratio of these two sides is the tangent. And the arctangent is simply the reciprocal of the tangent. So my angle is the arctangent of my capacitive reactance divided by my resistance. So I take this side, divide it by that side, take the arctangent or the reciprocal of the tangent, and that will give me this angle. So what are the numbers? Well, that's going to be equals to the arctangent of 26.53 over R. Fairly simple to do. It's a three-step process. So 26.53 divided by 30 equals, that number's useless, but I take the arctangent. So where's my arctangent button? Right there. And I got 41.48 degrees. And so remember when we did all those gyrations and figured out how all those sine waves lined up with each other just because of how that circuit works. If we freeze time and see that the circuit acts like a DC circuit, if we freeze time, we found that our current was leading the source voltage by 41 degrees approximately. Well, there we go, 41.48 degrees. So I did all those gyrations to show you why these things line up the way they do. I wanted to point out that a AC circuit acts exactly like a DC circuit if you freeze time. So all that happens under alternating current is the circuit is reacting to the changes in voltage. But at any moment in time, it just acts like a DC circuit. And we could take that circuit, analyze it like a DC circuit at different times, and see how those voltages all lined up. And we got this angle by lining those things up. We don't have to go through that. We understand why that happens. And now we know why this all works. So the steps to find out my impedance, how much opposition to current flow. And of course, I take this 40 ohms, divide that into 50 volts. I get 1.25 amps, which is my RMS current. And we know that the current has a phase angle of 41.48 degrees. Once again, how we did that was we calculated our capacitive reactance with this formula. Capacitive reactance equals the reciprocal of 2 pi times the frequency times the capacitance. Once we had that, we could use the Pythagorean theorem to see our resistance here, our reactance there. They make a right angle, and the Pythagorean theorem tells us the length of that line there, or we could have drawn it on graph paper, but we could do the calculation. And then this formula, the arctangent of our reactance over our resistance, gives us the phase angle, or the angle that the current leads the source voltage in this particular circuit. And just finish up here, how do we notate those things? Well, once we calculate our impedance and our phase angle, that would be expressed, in this case, we had an impedance of 40 ohms with a phase angle of approximately 41 degrees, and that's how we would write that out. Our impedance and our phase angle. There's another way to write this out that can be useful. This is called polar notation because we're looking at the angle. So let's draw our triangle again. So there's our triangle, and we're looking at this angle and the length of that line. The other way to express this is called rectangular notation, where I simply talk about the length of this line and the length of that line. And that would be expressed as, well, this is 30 ohms, and this is 26.53 ohms. So rectangular notation, I would say it's 30 ohms minus J, 26.53. So polar and rectangular notation. Now I use minus J because it's a capacitor. Now this is a complex number. If you're familiar with complex numbers, you would say, hey, isn't that a lowercase I? Well, normally it is, but in electronics, a lowercase I represents AC current. And so to avoid confusion, in electronics we use J, but in most mathematics they would use an I. So capacitive reactance, we use minus J. And when we get to inductors in AC circuits, we will have a plus J there because they go different directions. As a matter of fact, I have this backwards. I really should have that go down. So for capacitance, I should have the resistor horizontal and the capacitor goes down for a minus J whatever. And there's our hypotenuse. It still works, but for an inductor, I would be a plus J for my inductive reactance. And using this rectangular notation, if I have both inductors and capacitors, I can actually add those together working with this. So sometimes this is useful, but typically we express an impedance as a number of ohms and a phase angle representing the length of the hypotenuse of our triangle and the angle between our resistance and our impedance. And so that is how our resistor and capacitor interact with alternating current. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocatomy.net, you can go to patreon.com/join/vocatomy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.